So let's do a little bit more complicated one right now. Okay, so let's consider that we've got a large block of charge, and the charge is uniformly distributed throughout the block. So the charge has a volume charge density of 1.78 microcoulombs per cubic meter. And so I've got this very large block, and I'm going to assume that I've got a sphere inside here. And the sphere has a radius of 9.41 centimeters. So I want to know what is the total flux through that sphere. Okay, the sphere is embedded inside this block of uniform charge, and I want to know the flux through here. Now that's difficult because we've got charge inside here, we got charge here, we got charge there, we got charge there, we got charge here, we got charge over here. There's charge everywhere. Well, Gauss's law comes to the rescue. It says the total flux is going to be equal to the enclosed charge over epsilon naught. So what is the enclosed charge? Well, the enclosed charge is just the charge inside the sphere. So the charge inside the sphere is going to be the charge density times the volume of the sphere. So that's going to be the charge density times 4/3 pi r cubed. So the enclosed charge would be 1.78 times 10 to the minus 6 coulombs per cubic meter times 4/3 times pi times 0.0941 meters cubed. So the enclosed charge comes out to be equal to 6.21 times 10 to the minus 9 coulombs. So the flux is going to be 6.21 times 10 to the minus 9 coulombs divided by 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. And so the flux comes out to be 702 Newton meter squared per coulomb. Okay, and so that is a more complicated problem. But you see, even the more complicated problems using Gauss's law still are not as bad as the simple problems using chapter 22.